Welcome! In this video, we'll explore LeetCode problem number 1080, insufficient nodes en route to leaf paths. This problem challenges us to prune nodes in a binary tree based on a route to leaf path sum threshold. We'll break it down step by step to ensure you fully understand the approach. Let's dive right in. In this problem, we are given the root of a binary tree and an integer called limit. The task is to prune the tree by removing any root to leaf path where the sum of the node values along that path is less than the specified limit. Here, a path is simply a sequence of nodes starting from the root and ending at a leaf, and a leaf is defined as a node that has no children. If pruning a path leads to a node having no children left, that node should also be removed. The final output of the problem is the root of the pruned tree. If pruning results in an empty tree, we return null. The input format includes the binary tree's root, where each node has a value and pointers to its left and right children, and the integer limit. The output is the root of the updated tree after pruning. To better understand the problem, let's look at our first example. Here, the input tree has the root value 1, with children 2 and -3. Node 2 itself has a left child, -5, while node -3 has a right child, 4. The given limit is -1. The task is to prune any paths from the root to a leaf where the sum of the node values is less than -1. After pruning, the output tree is represented as 1, null, -3, null, 4. Now, let's analyze how the pruning works in this example. The original tree has two root to leaf paths. The path 1-2-5 has a sum of -2, which is less than the limit of -1, so this entire path is pruned. On the other hand, the path 1-3-4 has a sum of 2, which meets the limit, so we keep this path. The resulting tree, after pruning, is simplified to just the nodes 1, -3, and 4. This demonstrates how paths are evaluated and pruned based on their sums relative to the limit. In the second example, the input tree has more nodes and a limit of 22. The root node is 5, with children 4 and 8. Node 4 has a left child, 11, which itself has children 7 and 1. Node 8 has children 17 and 4, and the second 4 node has children 5 and 3. The goal remains the same, to prune any root to leaf paths where the sum of the node values is less than the limit. After pruning, the output tree is represented as 5, 4, 8, 11, null, 17, and we can visualize the changes in the tree structure. Breaking down the second example, we evaluate each root to leaf path and its sum. The path 5-4-11-7 has a sum of 27, which is greater than the limit, so we keep it. The path 5-4-11-1 has a sum of 21, which is less than the limit, so it is pruned. Similarly, the path 5-8-17 has a sum of 30, so we keep it. The path 5-8-4-5 has a sum of 22, meeting the limit, so it is also kept. However, the path 5-8-4-3 has a sum of 20, which is less than the limit, so it is pruned. The final pruned tree reflects these decisions, showing only the paths that meet or exceed the limit. Finally, it's important to consider edge cases in this problem. For instance, we may encounter trees with negative node values or a negative limit. If the tree has only one node and its value is less than the limit, the entire tree is pruned, and we return null. Similarly, if all paths in the tree have sums below the limit, the result is also an empty tree. On the other hand, if no pruning is required because all paths meet the limit, the output will simply be the original tree. These constraints and cases ensure the solution is robust and accounts for all possible scenarios. To solve the problem of pruning insufficient nodes en route to leaf paths, our goal is to traverse the binary tree and evaluate the sum of each path. If the sum is less than the given limit, the nodes in that path must be removed. The brute force approach is one way to tackle this. It involves computing all root to leaf path sums during a pre-order traversal. At each step, we calculate the cumulative path sum and, if it doesn't meet the limit, we backtrack to prune the corresponding nodes. This method is straightforward but inefficient, as shared subtrees may have their sums recalculated multiple times, leading to a time complexity of n² in the worst case. While easy to conceptualize, this redundancy makes it unsuitable for larger trees. A more efficient method is to use a post-order traversal, where we process the left and right subtrees before evaluating the root node. This bottom-up approach avoids redundant calculations by directly reusing the results of subtree evaluations. For each node, we calculate the maximum valid path sum from both subtrees. If both are insufficient, the node is pruned by returning null. Otherwise, the node's value is added to the greater of the two subtree sums to determine its own validity. This approach achieves a time complexity of O(n), as each node is visited only once, and a space complexity of O(h), where h is the tree's height. Alternatively, an iterative depth-first search leverages an explicit stack to simulate post-order traversal. While it eliminates recursion-related stack overflow risks, it requires careful stack management, making the implementation slightly more complex. Both approaches are efficient, but the recursive post-order traversal is often preferred for its clarity and alignment with the problem's requirements. We selected the post-order traversal approach as the optimal solution due to its efficiency and simplicity. By processing the tree bottom-up, we avoid redundant computations and ensure that pruning decisions are made only after fully evaluating a node's subtrees. This strategy not only minimizes computational overhead but also results in cleaner and more maintainable code. A key insight here is that the validity of a node depends solely on its subtrees and path sum. This makes post-order traversal a natural choice, as it allows us to prune subtrees before considering their parent nodes, streamlining the decision-making process. While iterative DFS is a viable alternative for very deep trees, its added complexity in stack management makes it less appealing for general use. The brute force method, though simple at first glance, fails to scale efficiently for larger structures due to its redundant operations. The final analysis of our chosen strategy highlights its balance of efficiency and simplicity. With a time complexity of O(n), we ensure that each node is processed exactly once, avoiding unnecessary recomputation. The space complexity is O(h), where h represents the height of the tree, and this accounts for the memory used by the recursion stack. This balance makes the post-order traversal approach not only efficient but also easy to implement and maintain. By combining clarity with optimal resource usage, this strategy effectively addresses the problem's requirements while remaining robust even for larger or more complex trees. The problem we're tackling is called insufficient nodes and root-to-leaf paths here. The goal is to prune nodes from a binary tree based on a given threshold called limit. A root-to-leaf path in this context refers to any sequence of nodes starting from the root and ending at a leaf node, where a leaf is a node with no children. The sum of the path is calculated by adding up the values of all nodes along that path. If all root-to-leaf paths passing through a node have sums less than the given limit, that node is considered insufficient and should be removed. To solve this, we use a recursive post-order traversal approach. This means we'll process the tree starting from the leaf nodes, moving upwards toward the root. By evaluating each node after its children, we can determine whether the node contributes to any valid path. If not, we prune it. The overall strategy involves defining a recursive function that calculates path sums and prunes subtrees as needed. Let's break this down into steps. First, we define the function DFS that takes a node and a running total of the path sum leading to it, called current_sum. If the node is null, there's nothing to process, so we simply return null. This forms the base case of our recursion. Once we establish the base case, the next step is to add the current node's value to the running current_sum and recursively process its left and right child nodes. We achieve this by calling the DFS function on node.left and node.right, passing along the updated path sum. These recursive calls return the pruned versions of the left and right subtrees, which we then assign back to node.left and node.right, ensuring the tree structure is updated in place. Now we need to handle leaf nodes specifically. If the current node becomes a leaf after processing its children, meaning both node.left and node.right are null, we check whether its path sum is less than the limit. If it is, the node is pruned by returning null. Otherwise, we retain the node by returning it. Finally, we initiate the pruning process by calling DFS on the root node with an initial path sum of 0. By processing nodes in a post-order fashion, we ensure that decisions about pruning are made only after evaluating all child nodes, making the algorithm both efficient and logically sound. This approach also ensures that internal nodes are only pruned if all their children are insufficient. There are several important edge cases to consider when implementing this algorithm. First, if the binary tree is empty to begin with, the output should simply be null. Second, if the tree consists of a single node, we check whether the value of that node meets the limit. If it doesn't, the entire tree is pruned. Lastly, if none of the root-to-leaf paths in the tree satisfy the limit, the result will be an empty tree after pruning. From a data structure perspective, the binary tree represents the input, with each node holding a value and pointers to its left and right children. Additionally, the recursive stack is used to manage intermediate nodes as we traverse the tree. In terms of complexity, the algorithm is efficient. The time complexity is O(n), where n is the total number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, because the recursive calls go as deep as the maximum depth of the tree. Analyzing an example will help solidify these concepts. Consider the input tree shown here, where the root node has a value of 1, and its left and right subtrees extend further with values as indicated. With a limit of 7, we start by evaluating the leaf nodes at the bottom of the tree. Node 4 has a path sum of 7, which meets the limit, so it's retained. Node 5 has a path sum of 8, which also meets the limit, so it's kept. Node 6 has a path sum of 10, making it valid as well. Next, we move up to process their parent nodes. For Node 2, both of its children, nodes 4 and 5, have valid paths, so Node 2 is retained. For Node 3, its child, Node 6, contributes to a valid path, so Node 3 is retained as well. Finally, we evaluate the root node. Since all paths in the tree meet the limit, the root is retained, and the tree remains unchanged after pruning. The final output tree is identical to the input tree, with all nodes retained. This example illustrates how the algorithm systematically evaluates and prunes nodes based on their contribution to valid paths, ensuring the resulting tree satisfies the problem constraints. Here, we begin by defining the structure of a binary tree node using the treeNode class. Each node contains a value, as well as references to its left and right child nodes, which are initialized as none by default. Next, we define the solution class in the sufficient subset method, which takes a root node and a limit as input. Inside this method, we define a helper function called DFS to perform a depth-first traversal of the tree. This function takes a node and the current path sum as arguments. If the current node is none, meaning we've reached the end of a path, we simply return none. Otherwise, we update the current path sum by adding the node's value. If the current node is a leaf, meaning it has no left or right children, we check whether the path sum meets or exceeds the given limit. If it does, we keep the node, otherwise, we return none, effectively pruning it. The helper function then recursively processes the left and right subtrees. After pruning, we reassign the left and right child nodes of the current node to the results returned by the DFS calls. If both the left and right subtrees have been pruned, meaning the current node no longer connects to any valid paths, we remove the current node by returning none. Otherwise, we retain the node. Finally, at the end of the sufficient subset method, we initiate the depth-first search by calling DFS on the root node with an initial path sum of 0. This ensures that the tree is processed from the top down, pruning any insufficient paths and ultimately returning the modified tree that satisfies the conditions. Here, we start by defining our solution class and the treeNode class, which represents the structure of a binary tree node. Each tree node contains an integer value, and references to its left and right child nodes. There are multiple constructors to initialize a tree node, including a default constructor, one accepting just a value, and another accepting a value along with left and right child nodes. Next, we define the main function, sufficient subset, which takes the root of the tree and an integer limit as input. This function calls a helper method, DFS, to traverse the tree and determine which nodes should remain. The DFS method is designed to perform a depth-first search. It starts by checking if the current node is null, in which case it returns null, indicating that this branch has been pruned. Now, we calculate the new cumulative sum by adding the value of the current node to the existing sum. If the node is a leaf, meaning it has no left or right children, we check if the path sum meets or exceeds the given limit. If it does, the node is retained, otherwise, it's pruned by returning null. For non-leaf nodes, we recursively process the left and right subtrees, updating the references to these child nodes based on the results of the recursive calls. After processing both subtrees, we check if the current node should remain. If either the left or right child is not null, the node is retained, otherwise, it is pruned by returning null. This ensures that only sufficient paths, where the sum meets the limit, are preserved in the tree. In this example, we start with the root node, which is 1, and initialize the current sum as 0. Adding the value of the root node to the current sum gives us a new sum of 1. From here, we move to the left child, which is the node with value 2. Adding 2 to the new sum results in 3. Next, we head to the left child of 2, which is 4, and adding 4 to the current sum gives us 7. Since node 4 is a leaf and the sum from root to this leaf, which is 7, meets the limit of 2, we retain this node. Now, we backtrack to node 2 and explore its right child, which is -5. Adding -5 to the sum from node 2 results in -2, which is less than the limit. As a result, we prune this node and remove it from the tree. After pruning the right child of node 2, we backtrack to the root node, 1, and move to its right child, which is -3. Adding -3 to the sum from the root gives us -2. Since node -3 is a leaf and the path sum of -2 does not meet the limit of 2, we prune this node as well. Now, at the root node, the right subtree is completely pruned, but the left subtree remains intact. The final tree structure after pruning looks like this: the root node 1 has a left child 2, and that node has a left child 4. In array representation, the tree is 1, 2, null, 4. In the second example, we begin with the root node, which is 1, and initialize the current sum as 0. Adding the value of the root node to the current sum gives us a new sum of 1. From here, we move to the left child, which is the node with value -2. Adding -2 to the current sum results in -1. Next, we move to the left child of -2, which is -4. Adding -4 to the current sum gives us -5. Since this is a leaf node and the sum from root to this leaf, -5, does not meet the limit of 0, we prune this node. We then backtrack to node -2 and move to its right child, -5. Adding -5 to the current sum gives us -6. Similarly, this value is less than the limit, so we prune this node as well. With both children of node -2 pruned, we remove node -2 entirely. At the root node, we now move to the right child, -3. Adding -3 to the current sum results in -2. Since -3 is a leaf and its path sum is below the limit, we prune this node as well. Finally, with both subtrees of the root node pruned, the root itself is removed, leaving us with an empty tree. The output is. In this third example, we start at the root node, which is 5, with a current sum of 0. Adding 5 to the current sum gives a new sum of 5. We then move to the left child, node 4, and add its value to the sum, resulting in 9. Next, we move to the left child of 4, which is node 11. Adding 11 to the sum gives us 20. Moving further down, we reach node 7, which is a leaf node. Adding 7 to the sum gives us 27. Since 27 meets the limit of 22, we retain this node. Now, we backtrack to node 11 and move to its right child, which is node 1. Adding 1 to the sum gives us 21. As 21 is less than the limit, we prune this node. At node 4, the left child remains, but the right is pruned. We then backtrack to the root node and move to the right child, node 8. Adding 8 to the sum gives us 13. From here, we move to the left child of node 8, which is node 13. Adding 13 to the sum results in 26. Since 26 meets the limit, we retain this node. Back at node 8, we now move to the right child, node 4. Adding 4 to the sum gives 17, and moving further down to its right child, node 1, gives a sum of 18. Since 18 is less than the limit, we prune this node. At node 8, only the left child, node 13, is retained. The final tree structure after pruning has the root node 5, with a left subtree containing nodes 4, 11, and 7, and a right subtree containing node 8 with its left child 13. The output for this example is 5, 4, 8, 11, null, 13, null, 7. This represents the pruned tree structure where nodes that did not meet the path sum limit of 22 have been removed. The tree now contains only the paths that satisfy the condition, demonstrating how the algorithm successfully eliminates insufficient nodes while preserving valid paths. The time complexity of this solution is O(n), where n represents the number of nodes in the binary tree. This is because the algorithm uses depth-first search, or DFS, to traverse the entire tree. During this traversal, every node is visited exactly once, and for each node, the operations performed, such as determining if it's a leaf, updating the cumulative sum, or pruning subtrees, take constant time, or O(1). When you multiply the constant time per node by the total number of nodes, you get a time complexity of O(n). Mathematically, since each of the n nodes is processed independently, the total cost scales linearly with the size of the tree, reinforcing the O(n) complexity. The space complexity of this solution is O(h), where h is the height of the binary tree. This is due to the recursion stack that is created during the DFS traversal. The depth of the stack corresponds to the height of the tree. In the best-case scenario, where the tree is balanced, the height is approximately log n, leading to a space complexity of O log n. In the worst-case scenario, where the tree is completely skewed, the height becomes n, resulting in an O(n) space complexity. Since no additional data structures are used beyond the recursion stack, the space complexity is entirely proportional to the tree's height. Across the best, average, and worst cases, the time complexity remains O(n), while the space complexity ranges from O log n for balanced trees to O(n) for skewed trees. To compare this approach with a naive method, consider a brute force solution that generates all root-to-leaf paths, calculates their sums, and prunes nodes based on the results. This approach has a time complexity of O(2 to the power of h, due to the exponential number of paths in a binary tree of height h. It also requires O(h) space to store a single path. In contrast, our optimized approach leverages DFS and prunes subtrees dynamically, achieving a linear time complexity of O(n) and a space complexity of O(h) proportional to the tree's height. The efficiency of this method is evident when you consider the mathematical proof. Each node is visited exactly once, resulting in O(n) operations, and the recursion stack depth corresponds to the tree height, yielding O(h) space complexity. Whether the tree is balanced or skewed, this solution provides an optimal balance of time and space efficiency for processing binary trees. Here we discuss some common mistakes developers make when solving this problem. First, not handling leaf nodes properly can lead to errors. It's easy to assume that every node without children is a valid leaf, but if the path sum leading to that leaf is smaller than the given limit, the leaf must still be pruned. Another mistake is failing to update parent-child relationships during pruning. If you remove a node but forget to disconnect it from its parent, this can cause dangling references or null pointer errors, especially in languages like Java or C++. Next, using pre-order traversal instead of post-order traversal is a common pitfall. Pre-order evaluates and prunes nodes before processing their children, but since you need the path sums for all descendants to make a decision, post-order traversal, where you process children first, is the correct choice. Lastly, ignoring edge cases like an empty tree, a single node tree, or a very small limit can result in runtime errors or incorrect outputs. Proper testing ensures your solution is robust against these scenarios. Another mistake to avoid is the inefficient recalculation of path sums. If you compute the same path sum multiple times for different nodes, it leads to redundant calculations and increases the problem's time complexity unnecessarily. Now, let's look at some interview insights. A key takeaway is the importance of post-order traversal, processing nodes in left-right root order, especially in tree problems where decisions depend on child nodes. This traversal pattern is common in similar problems, like delete nodes and return forest, problem number 1110, which also emphasizes recursion in tree pruning. Practicing these types of problems helps strengthen your recursive thinking. During interviews, be prepared to discuss why post-order traversal is optimal for this problem and how you minimize redundant calculations. Additionally, interviewers often explore edge case handling, so it's important to clearly explain how your approach safeguards against issues like null trees or single-node trees. Now let's connect this problem to related ones. For example, LeetCode number 1110, delete nodes and return forest, is another tree pruning problem that requires careful subtree checks. LeetCode number 112, path sum, is foundational for understanding root-to-leaf path sums, while LeetCode number 113, path sum 2, focuses on finding all valid paths instead of pruning. Finally, LeetCode number 437, path sum 3, examines path sums in any part of the tree, not just root-to-leaf paths. As for alternative approaches, one option is using a helper function to calculate path sums in a separate pass before pruning. This can simplify debugging but requires two traversals, which increases time complexity. Another strategy is an iterative approach using a stack to manage traversal and pruning. While this avoids recursion depth limits, it can be more complex to implement and debug. Finally, dynamic programming can be applied to cache intermediate path sums and avoid recomputation, but this increases space complexity. Each approach has trade-offs, so choose based on the constraints of the problem and the programming environment. Great job! Today, we tackled LeetCode number 1080, learning how to prune a binary tree based on root-to-leaf path sums. Remember, recursive tree traversal is key here. Thanks for watching, and don't forget to like, comment, and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!